Let's begin. Hello everyone, I'm Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So we'll go over the contents of week 6. Before that, we'll just go over the questions of week 5, and then we'll go over the contents of week 6. Okay. So let's start. So last week, I think I discussed this. We'll just go over a summary so that you understand when the questions are being solved. Am I audible? Just checking. Can someone just tell me if I'm audible? Okay, thank you. Yeah, thank you. So what we discussed in week 5 was directional stability and lateral stability. Till then, we had discussed the longitudinal static stability, and then we moved on to the other axis. Okay, so the conventions for directional stability is that right wing back is considered positive yawing moment. Okay, so when the aircraft is like this, and when it turns, I mean, if its wings turn that way, right? This is considered positive yawing moment, right wing back. Okay. So, and then when you have, if this is your forward velocity and this is your gust, this is considered positive side slip angle beta. Okay. This is negative. Okay. So if your relative velocity vector is on the right, you have positive beta. If it's on the left, it's negative beta. Then the control surface convention, if you deflect your rudder to the left, so where is your rudder? This is your fuselage reference line, and this is your rudder. You deflect it to the left, right? Force is produced in which direction? To the right or the left? If I deflect my rudder to the left, along this area, is the force produced in towards the right or the left? Towards the left. Okay, so force is produced here, right? Because you're deflecting your rudder this side. So you have a camber increase in that direction. You have a force produced towards this. So this is your Fy, correct? Yes. So just before that, your Y direction, positive Y direction is this. Okay. This is your positive Y. So when you deflect your rudder to the left, the force produced is positive Fy. Okay. And hence, if this is your CG, it produces yawing moment to the left. Okay. So conventions are right wing back is considered positive yaw. Velocity vector, relative velocity vector to the left, to the right is considered positive. Rudder deflection left is considered positive, and the aircraft yaws left. Okay, these are your conventions. Okay. Now for stability, what do we need? What happens when the aircraft, so if this is your original relative velocity, and then it encounters some crosswind or gust, and it becomes in this direction, and you have a positive beta. So if this was your fuselage reference line, you have a positive beta. Okay. So to negate the beta, what kind of moment do you need? You need to make the beta 0. What do you do? How do you turn your aircraft such that the beta becomes 0? This is your CG. Do you turn this side or do you turn this side? Do you turn clockwise or anti-clockwise? To make beta negative, 0. Which side do you turn? Which side do you yaw to make the beta 0? So you were flying straight and then you are met with some beta. You need to make this beta 0. You can't change the direction of the wind. You can only rotate your aircraft. So do you rotate your aircraft clockwise, counterclockwise, or do you positive yaw, negative yaw? Because of this positive beta, do you do positive yaw? Yeah, okay. So let me just try erasing this 1 second. This was your original fuselage reference line. This was your aircraft. Pardon me for the drawing. This was your original velocity. Now, due to crosswind, your velocity has become like this. That means it is a positive beta, correct? So this is positive beta. Now, if this is your CG, which should the aircraft your left or right to negate this beta, to make the beta 0? You want beta to become 0. So do you turn your aircraft to the right or the left? To the right, exactly. So you need a right yaw. So you need a positive yaw, correct? Yaw towards the right is positive. Yes. So for a positive beta, you need a positive yaw. Yawing moment is represented by N. So the Cn beta is nothing but Bcn by D beta. For a positive beta, you require your yawing moment to be positive. Hence, this is greater than 0. Okay. That is what is required for static directional stability. The inherent ability of your aircraft to negate the effects of crosswind is known as static directional stability. Okay. So if your aircraft is encountered with a positive beta, if your aircraft is directionally stable, it will produce a positive yaw. It will yaw towards the right. Okay. Okay. Now we'll check out the forces that are produced when it's met with a positive beta. So when it's met with a positive beta, what are the forces that are developed? So this is your fuselage reference line, and this is your tail. So because of this positive beta, which direction will the force be acting? It will be on this direction, right? So this will be your Fy. Because of the positive beta, you have Fy in this direction. Is that positive Fy or negative Fy? This Fy that I've written on the slide, is it positive or negative? Exactly, it's negative. Because your positive Y is in this direction. This is your positive Y axis. So due to a positive beta, the force produced on the tail is negative. Fy is negative. Now this negative Fy about this CG, will it produce a positive yaw or negative yaw? The yawing moment, N, will it be positive or negative? Exactly, it will produce a positive yaw, right? So this is the yaw that is produced. This is your Cn or N. So it produces a positive yaw. It yaws towards the right. So therefore, positive beta gives you negative force and positive yawing moment. Okay. You don't have to remember this. You can just easily draw this diagram and find out by yourselves. Okay. So what we see here is that this Fy is negative, right? So this is less than 0. But you require, for a stable aircraft, you require Cn to be positive. So when this is the formula of the Cn and your Cy beta is negative, that is why there is this negative sign here. We had discussed this even in the last session. So that is why there's a negative sign, that do not get confused. It's negative because your Cy beta is negative and you require, for stability, you require Cn to be positive. Okay. So similarly, the Cn beta also has that negative sign. That is because this Cy beta is negative. Okay. Now, some of the structures on the aircraft that contribute towards the directional stability are vertical tail. Vertical tail, we know just now we saw that when it encounters a positive beta, it produces negative force, which in turn gives you a positive Cn, which is what we require. We require Cn beta. Now, for the longitudinal case, our only condition for stability was what? What was the only condition for stability in the longitudinal case? Longitudinal static stability, single condition. What was it? Longitudinal static stability, what we discussed in the first 4 weeks. The pitching moment, angle of attack, elevator angle, so that one. What was the only condition for static stability in the longitudinal case? What is the only condition for stability in the longitudinal case? dCm by d alpha should be less than 0. Perfect. Okay. In our directional stability case, the only condition is that C and beta should be positive. Okay. So it's analogous to your longitudinal case. Longitudinal case, like Sandra said, dCm by d alpha should be less than 0. In the directional stability case, dCn by d beta should be greater than 0. Okay. So the factors or the structures on your aircraft that contribute towards this stability is vertical tail. Vertical tail we just saw. Positive beta produces negative force, produces positive Cn. Hence, Cn beta is positive. Another thing that produces positive Cn beta is the swept wing. Why does it do that? When there is a positive beta, the drag on the right wing increases, right? Because of the positive beta, the drag on the right wing increases. Lift also increases, but simultaneously drag also increases. Because the drag on the right wing increases, it creates a positive yaw. Okay. So vertical tail and swept wing, both of them contribute towards directional static stability. All right. Okay. Let's go to the next slide. Now here we look into the control aspect. So positive rudder deflection we know was deflecting it to the left. Deflect the rudder to the left, it produces a positive Fy, which produces a negative Cn. Do you remember that? Let me just draw that again. This is your fuselage reference line. This was your tail. And if I deflect my rudder to the left, it produces force. This Fy is positive. This Cg, and it produces a negative yawing moment. Okay. So dCn by d delta r is less than 0. For positive rudder, your moment produced is negative. Okay, which is why your Cn is Cn delta r is negative. All right. Now, similar to the longitudinal case, you have tau, control surface effectiveness parameter. Here it is dou beta by dou delta r. There it was dou alpha t by dou delta e. Right. So there it was d alpha tail by d delta e. Similar parameter. Okay. Then we just look at the formulas for Cn and Cn delta r. Very similarly derived as compared to the longitudinal case. So you can just follow the same steps and get these formulae. The sign conventions, you need to be very careful. So now when the lateral case comes, you have more sign conventions. So just don't try to memorize it. Just see how you can come up with the sign conventions. Okay. So just a comparison between the longitudinal and directional cases. For static stability in the longitudinal case, only condition, just like Sandra pointed out, is Cm alpha should be less than 0. Directional case, Cn beta should be greater than 0. In the longitudinal case, what was the condition for trim? You wanted to trim your aircraft at positive angles of attack. Hence, your Cm naught should have been positive. Okay, we had discussed this extensively. I think it's clear now. In the directional case, you want to trim your aircraft at 0 beta. You wanted to trim at the straight point. Okay, and your vertical tail is almost always symmetric. So you want to trim your aircraft straight, then your beta should be 0. So your Cn naught is almost always 0. Okay. Okay. And Cn naught, Cm naught, both of these parameters have nothing to do with stability. They are just to trim your aircraft at whatever desired angle. Okay. For stability, there is only one case, that is Cm alpha and Cn beta. Now control. For control, in the case of in longitudinal case, your Cm delta E is 0. Why? Why was it 0? So is less than 0. Why was it less than 0? This is your fuselage reference line. This is your horizontal tail. And if I deflect my elevator down, elevator deflection downwards, positive or negative? Downward elevator deflection, is it positive or negative? Can someone tell me downward elevator deflection, positive or negative? What was the convention? If I deflect the elevator down, was it positive or negative? What was the convention? In this case, if I deflect the rudder to the left, it is positive. What about for longitudinal case? Okay, downward deflection of elevator is positive. That is your convention. Okay. Do not forget these conventions. Downward deflection of elevator is positive. Okay. Okay. So if I deflect this elevator down, it is positive delta E. Produces, because of the increase in the effective camber, it produces an extra lift. So you have positive delta L. Okay. And if this is the CG of your aircraft, it produces a nose down movement. Nose down is positive or negative? Nose down moment, M. Positive or negative? Negative, correct. So positive deflection of elevator produces negative pitching moment, which is why your Cm delta E, which is dCm by d delta E, is negative. For positive elevator deflection, Cm is negative. So that's why your Cm delta E is negative. So that is the control derivative. In the case of directional stability, control derivative is Cn delta R. It should be negative. It will be negative. Okay. So that is what we just saw in the above few equations. Okay. Now let's go to lateral stability and control. What are the conventions? Right wing down is considered positive roll. So this is your aircraft. This is how it was. Right wing down. This is considered positive roll. Okay. So how do you identify which is positive roll, positive yaw, positive pitch? You put your right hand thumb rule. Okay. So you put your thumb along the rotational axis. The direction of the curl of your fingers gives you the positive rotation. Okay. Okay. So if I put it along the longitudinal axis towards the nose, rolling towards the right or rolling in the clockwise direction is considered positive. Okay. Similarly, when I deflect my right aileron up, left aileron down, it produces a positive rolling moment. And this is considered positive delta A. Delta A is deflection of elevator. Okay. Deflecting right aileron up, left aileron down, it's considered positive delta A. It produces a positive rolling moment. Okay. Okay. Now for static lateral stability, what are the conditions required? For a positive roll, you require CL to be less than 0. Okay. Like if the aircraft rolls towards the right, you want it to roll back. So your CL should be less than 0. Okay. Now if it banks right, the force produced is negative Fy. Let me try to elaborate that. It's very well explained in the lectures. Let me just try to elaborate that. So when it banks towards the right, you have an effective positive beta. Okay, so when this happens, this condition, okay, that condition when it happens, there is an effective positive beta. For bank right, you have a positive beta. Okay. When the positive beta happens, what direction was the force generated? You had negative Fy, correct? Just like in the previous slide. Where was it? Yes, here. You had a negative Fy for positive beta. This is negative. For positive beta, you had negative Fy. Okay. So when you have negative Fy and it's produced at the vertical tail, and the vertical tail is placed above the fuselage. Okay, so your aircraft is something like this. Okay, so here is where the force acts and acts in this direction. This is your Fy, but your CG is along here. So it produces, how I'm not sure how I can tell you this. If this is your aircraft and this is your vertical tail, there is a force acting in this direction. It produces a rolling moment, correct? Restoring rolling moment. Okay. Do you understand? So there is a force acting in the upward direction towards the left, but since it is above the CG, it produces a negative rolling moment. It produces negative CL. Is that clear? So it produces something like this. Wait, let me, not sure, okay. Okay, so if this is your aircraft, is this visible? Is this phone visible? Yes, okay. If this is your aircraft and this is your vertical tail, okay. So because of a positive beta, you have a force in this direction. My finger, my pointer finger. Yes? Yes, okay. Now when this force, and if your CG is on your aircraft, your force is acting here. So force is acting in this direction. CG is on your aircraft. So it will produce anti-clockwise motion, which will rotate the aircraft. Is that clear? Yes, okay. Is it clear for everyone that a negative Fy acting at the vertical tail that is above your CG will produce a anti-clockwise moment? Yes, I hope it's clear. Just stop me at any point if it's not clear, okay? So positive, for a bank, right, it produces an effective positive beta. Positive beta, we know, produces negative Fy. This negative Fy above your CG produces rolling moment. Produces negative or restoring rolling moment, okay? So for a laterally stable aircraft, your CL beta should be negative, okay? Yeah, this is only when the vertical tail is above. This happens only when the vertical tail is above. What happens if your vertical tail was below? So this is your aircraft and the vertical tail is here. So the force produced would be below the CG, correct? Now this will produce a positive roll. Is that clear? So your force is here, right? And it will produce a positive roll. So it will not contribute towards lateral stability. Is that clear? Only when your vertical tail is above, that is only when this Fy, negative Fy is produced above your CG, only then it will produce restoring moment. Otherwise, if it's below, it will further deviate from your desired point. Okay, it will not roll back. Okay, so it is stable only when your vertical tail is above. Okay. Similarly, similar to the directional case, you have an expression for CL beta. Here, the negative sign is not there because you understand that it requires to produce a negative sign. So effectively, this is negative and you require your CL also to be negative, which is why you are not substituting a negative sign here. Okay. And just don't confuse. The previous case has a negative sign only because you require your CN to be positive. Okay. I'm just trying to make that clear. Okay. So similar to the directional case, the structures that contribute towards lateral stability are vertical tail. Vertical tail when it is above your aircraft, which is the typical configuration. Then high wing produces CL beta, which is less than 0. Okay, so let me try to explain that. If this is your aircraft, okay, not mid wing, 1 minute. If this is your aircraft and it rolls towards this side. So there is a component of the oncoming force, oncoming velocity that produces a force in this direction, making it roll back. Now, if it is for the low wing condition, that force is acting here. Okay, so there is a component of force acting in this direction, which will continue towards, it will not produce any restoring moment. It will continue destabilizing your roll, which is why high wing has CL beta negative, has CL beta that is contributing towards stability, lateral stability. So high wing is more laterally stable as compared to low wing. Now, the low wing can also be made stable. How? When you give it a dihedral angle. What is a dihedral angle? So this is your regular low wing. If you have a dihedral, you have something like this. Okay. So this is explained in the lectures again. I'm just summarizing it. When you bank right, it produces a positive beta. And because of this positive beta, there is an increased angle of attack on the right wing. Okay, this wing has an increased angle of attack that produces a negative or restoring rolling moment. Okay, so the structures that contribute towards lateral stability, vertical tail which is above, high wing or low wing with a dihedral. Okay, remember this. For the previous case, it was vertical tail and swept back wing, swept wing. Okay. Now let's look at some questions. This I had discussed in the last session, but a lot of people weren't there. So I said I will discuss it again in this week. During a flight, if the aileron is deflected with a certain positive angle, how will this affect the directional stability of an aircraft? Will it increase? Will it decrease? Will it remain unchanged? Or you cannot say. When aileron is deflected with positive angle. Read the question, think about it for a minute and tell me. Read the question carefully. Yes, okay, if you say it won't affect, okay, Sandra says unchanged. Can you try to justify your answer? Just try. Exactly, that's perfect. So because it's a control surface, it only changes your trim. If you want to trim at a different location, different angle, different velocity, it only changes that. The stability is only governed by inherent properties, and that is what, in this case, it is directional stability, so it's C and beta. Control surfaces do not affect stability in any way, similar to the longitudinal case, okay? So it will remain unchanged, you are absolutely right. Okay. The contribution of vertical tail to directional stability depends upon vertical tail volume ratio, vertical tail efficiency factor, both these options or none of these. Contribution of vertical tail to directional stability. Vertical tail contributes towards directional stability. Yes, we just saw it. It is not a control surface. The entire vertical tail, the structure affects the directional stability. Now, which factors affect it? Vertical tail volume ratio, which is VV, vertical tail efficiency factor, eta VT, both of them or none of them? Which one is the right answer? Okay, so the equation is this. Can you try and tell me now? Both, exactly. So you have VV here, you have eta V here, so it is both. Correct, perfect. Okay. The aileron control effectiveness depends upon lift curve slope of wing, lift curve slope of vertical tail, lift curve slope of horizontal tail, none of these. The lift curve slope does come into play in control effectiveness, correct? So of what? Wing, vertical tail or horizontal tail? Wing, yes. The ailerons are on the wings. So it will, the lift curve slope of the wing is what is going to affect the aileron's effectiveness. Perfect. Okay. Primary control for adverse yaw recovery is? Rudder, yes. What is adverse yaw? This is a question I asked in the last session. Can you try and tell me what is adverse yaw? Yaw, we know it's the motion along the z-axis. It's the rotation along the z-axis. What is adverse yaw? What is adverse yaw? I had asked you to look it up in the last session. Can you try to tell me what is adverse yaw? Yaw when roll happens. Okay, yes. Why? Why is it called adverse? Adverse is giving you a negative connotation, something that is not desirable, right? So, yeah, so why do we not like the yaw that happens when you roll? Okay, so before that, tell me, if I roll towards the right, adverse yaw is happening to the left or the right? If I'm rolling, if this is my wing, I'm rolling to the right. So adverse yaw is happening to the left or the right? If I'm rolling to the right and the yaw happens to the right, it's desirable, right? It's good for me. Then I can turn towards the right. So why is it called adverse? I'm rolling to the right. I'm also turning to the right. It's good for me. Why is it that? Yes. The yaw that is produced in the opposite direction to that of roll is called adverse yaw. Why is it happening? Why is it happening in the opposite direction? Any guesses? Any idea? When I roll to the right, why is my yaw going to the left? Why is the adverse yaw happening? Try and think about it for a minute. The drag on the opposite. Drag on the same wing, in fact, right? Wing tip. On the wing, the drag on the opposite wing. Drag on both of the wings have uneven profile. Okay. So it is pulled back more on this side. So let's just try and see this video. Let me know if you can hear it.
An aeroplane in straight and level flight has a lift distribution pattern that looks something like this.
Is it audible?
An aeroplane in straight and level flight has a lift distribution pattern that looks something like this. The lift generated by one wing is the same as the lift generated by the other wing. Deflecting the right aileron down causes an effective increase in the wing's camber and an increase in the effective angle of attack. The lift from that section of the wing increases. Deflecting the left aileron up causes an effective decrease in the wing's camber and a decrease in the effective angle of attack. The lift from that section of the wing reduces. The primary effect of aileron deflections is a roll. This is an approximate drag distribution pattern. When the ailerons are deflected, extra drag is generated by both wings. However, more drag is generated by the downgoing aileron than the upgoing aileron. This is induced drag, and it is caused by more lift required on the right wing to help initiate the roll. Combining the lift and drag effects together creates the undesirable tendency for the aeroplane to roll in one direction, but yaw in the opposite direction. This effect is called adverse yaw.
This is exactly what Sandra said. The drag on the opposite wing is what she said, but it's like the uneven distribution of the drag forces. When the lift is also changing, drag is also uneven. So when you roll towards one direction, because of the uneven drag, it yaws in the opposite direction, which is not what we need. We don't want our aircraft to roll in this direction, but turn in this direction. Okay. So now they go on to tell another reason, but let's just continue watching this video.
This effect is most noticeable at low speeds and on aeroplanes with high aspect ratio wings. There is another reason for the adverse yaw that is not often mentioned. In straight and level flight, both wings encounter the relative airflow head-on. But as the aeroplane rolls and the left wing moves down, a small amount of additional airflow strikes the wing from below. As the right wing moves up, a small amount of airflow strikes the wing from above, and vice versa. So as the aeroplane rolls, the relative airflow is deflected slightly up on the right wing, and the relative airflow is deflected slightly down on the left wing. As lift always acts at right angles to the relative airflow, the upward deflection of the relative airflow on the right wing causes lift to deflect backward. Conversely, as the left wing goes down, its relative airflow is deflected downward and its lift is deflected forward. The slight deflection of both lift vectors results in an adverse yaw moment to the right. The adverse yaw moment is felt when the aeroplane is rolling, and it stops when the aeroplane stops rolling. Adverse yaw can be prevented by using the rudder to create a yawing moment that helps to turn the aeroplane in the correct direction to remain coordinated. Some aeroplanes incorporate design features to minimise the adverse yaw. One such feature is called differential ailerons. By excessively deflecting the upward aileron, drag is increased on the downgoing wing. This produces a desired yaw force in the direction of the turn.
Okay. So is that clear? The multiple reasons for adverse yaw and multiple ways to overcome it. Yeah, I hope it's clear. Okay.
An aeroplane.
To the next question. For a conventional aircraft, the sign of CL delta A and CN beta. Think about it, write it down and tell me. CL delta A, let's start with CL delta A, is dCl by d delta A. Now, what was positive delta A? What was positive delta A? This is, I had marked this as positive delta A, right aileron up, left aileron down, right? So this is positive delta A. Let's just look at it, right aileron down up. Right aileron up, left aileron down. Okay, this is positive delta A. Now tell me what CL will this produce, positive or negative? Right aileron up, left aileron down. Will it produce positive or negative rolling moment? Negative. If I deflect my right aileron up, the lift on the right wing, let me just draw this. If I deflect my right aileron up, lift on the right wing increases, it reduces. On the right wing. Lift reduces, no? Exactly. What about the left wing? When I deflect the aileron down, the lift increases. Yes? Yes. So this produces a clockwise rolling motion. Now that is positive or negative? Put your thumb along the roll axis, your fingers curling. Positive, exactly. So this produces a positive L or rolling motion. So positive delta A gives you positive CL. So this is greater than 0. Correct? Yes. Now let's look at CN beta. It's dCN by d beta. The first one was a control derivative. This is a stability derivative. Okay. So this is positive beta. Correct? Does this produce positive or negative yaw? This is positive beta. Positive beta produces Fy, correct? Produces negative Fy. Now, does this produce positive or negative yaw? Positive yaw, correct. So it produces positive N. So this is also greater than 0. So both of them are positive, correct? Yes. Okay, now look at this question. An aircraft is flying in the south direction at a velocity of 50 meters per second under crosswind from west to east of 3 meters per second. The side slip angle in degrees will be. So usually when we draw this, when we draw an aircraft, what we see is that we show the wind is coming here. Wind is coming onto this one on the aircraft. And the crosswind is here, and this is considered positive beta. Okay. Now they're saying the aircraft is flying south. Okay. So the wind is flying from south to north. Aircraft is flying towards the south. So the wind will be from south to north. Yes. That is clear. If the aircraft is flying towards the south, the wind is coming in this direction, reverse, no? So it will be from south to north. Yeah. So if I draw the wind, sorry. So the wind direction is from south to north. So this is south, this is north. Okay. So then this would be west, this would be east. Is this clear? So it says it's flying south at a velocity of 50 meters per second. Okay. Yes. Yes. So now they say south direction at a velocity of 50 meters per second is done. Now crosswind from west to east of 3 meters per second. So you have something like this. 3 meters per second. Okay. So how will your relative velocity be now? This was your initial relative velocity. Now how will it be? It will be something like this. Yes. So, and this would be your beta. The angle that the relative velocity makes with the fuselage reference line is beta. Will it be positive or negative? Will it be positive or negative? It will be positive beta, right? So this is your regular conventional case. This is conventional, as in what we usually do demonstrate while teaching. So this is what is the question. This is in the question. Okay. So if you just rotate it around, you know that this is your positive beta. Is that clear? Just try rotating it in the north direction. You will see that the velocity vector is towards your right, and that is your positive beta. Okay. Now, how do you find out beta? How do you find out beta? Beta is, can you tell me the value or tell me the equation? How do you find out beta? It's a very simple, it's just a right angle triangle. Can you find out beta? It will be tan inverse. What upon what? I'll give you a minute to try and do this. From this diagram, from this triangle, what is it? Tan inverse? Tan inverse 3 by 50, right? Opposite by adjacent. Opposite is 3 and adjacent is 50, correct? Am I audible? Is this not clear? Can someone confirm if I'm audible? Am I audible? Can you hear me? Am I audible? Can someone just confirm? Just tell me. Can you tell me if I'm audible? Can you hear me? Can you see me? Just put it up on the chat box. Am I audible? I'm just going to presume I'm audible and continue since none of you are responding. Okay, so if I do tan inverse 3 by 50, I get 3.433 degrees. Yes? So it's positive and it's 3.433 degrees. Moving on to the next question. An aircraft is flying in the south direction at a velocity of 60 meters per second under crosswind from west to east of 6 meters per second. Similar to the previous question, very similar to the previous question, in fact, till finding beta. If the value of Cn beta is 0.015 per degrees and Cn delta R is minus 0.09 per degrees, notice that Cn beta is positive and Cn delta R is negative, so it's a conventional aircraft, where beta is the side slip angle and delta R is the rudder deflection. The rudder deflection in degrees given by the pilot in this case will be, what is the rudder deflection? Why do we need control surface deflections? What is the purpose? What do we accomplish? Why do we do control surface deflections? It's obviously not contributing towards stability. Sandra had said that clearly. What do control surfaces do? Why do we deflect? Why do we deflect the control surfaces? When somebody new has joined, can you tell me if I'm audible? Just tell me that. Am I audible? Thank you. Thank you for confirming that. Okay. So this is just like the previous question as far as finding beta is concerned. But when you they've asked you the rudder deflection in degrees given by the pilot in this case. You deflect your elevator or rudder or aileron, whatever, to trim your aircraft to different conditions. Okay. So you deflect your rudder in this case to trim the aircraft. So what happens is that your N needs to go to 0. N is your yawing moment. Okay, that's why you deflect your rudder. So the equation for Cn is Cn delta R into delta R, the control surface, plus Cn beta into beta. Now this has to go to 0. So they've asked you what is the rudder deflection so that this equation goes to 0, so that the yawing moment becomes 0. What is that? Trim. Okay. At trim, Cn becomes 0. So they've asked you what is the rudder deflection so that your Cn or N, that moment is trimmed, the moment goes to 0. So this is what you need to find out. What is delta R then? It will be minus Cn beta by Cn delta R into beta. Cn beta, you have. Cn delta R, you have. What you don't have is beta. Can you try and find out beta? I'll give you some time to do that. Just like the previous question, try find beta. It's just like the previous question. So the aircraft is flying in the south direction. What does that mean? That the wind is going from south to north, correct? So this is your north, this is your south, this is your west, this is your east. So at the relative velocity is going from south to north at a velocity of 60 meters per second. Now crosswind from west to east, exactly like the previous question, west to east, and it is 6 meters per second. So this becomes your new relative velocity. And this becomes your beta, which is positive. Okay. Now try and find out beta and tell me delta R. Find beta, just let me know beta. It's a simple right angle triangle, just find out beta. Find out beta. Simple tan theta, just tan beta, just find out, write the equation for tan beta and you can find it out. So can you at least tell me the answer for this? Just do the calculation. It's a very simple. Just do tan inverse 6 by 60, tan inverse 1 by 10. Thank you. Thank you. So it's 5.71. Thank you. And it's degrees. Okay. So I substituted here. And since both of these C and beta and C and delta R are all per degrees. So it will just cancel out. Okay, so just substitute here. C and beta is 0.015 and C and delta R is minus 0.009. Beta, you've just told me, is 5.71. If you do this substitution, just put in the values. I just try calculating it. Let me know if I'm making any mistakes. Okay, I'm not using a calculator, it's just my phone. Okay, so upon number we get 9.516. That's the number. Okay, you get 9.516. Yes, yes. Okay, so is this clear? You find out beta, you put it into this equation, so and you get the Cn to be 0 because you deflect your elevator, rudder, all the control surfaces so that you can get trim. Okay, so that happens when you write this equation, set it to 0. Now you need to find out beta because that is the only other unknown in the equation. Find out beta from the information that is given to you. It's flying south. You have a crosswind. Put it. It's a simple tan inverse equation. Put it. Find beta. And then you put in this equation. Find your delta R. So this is the elevator deflection, rudder deflection required to trim your aircraft given these conditions. All right. Yes, these are the equations that we used. Okay. Now look at these questions. This is from your assignment 5. Consider the following aircraft. They've given you the weight. They've given you S, the area, the cruise altitude, density. They've given you aspect ratio of the wing. XCG is equal to XAC of the wing. XCG of the aircraft is the XAC of the wing. Is 0.32. They've given you mean aerodynamic chord 0.48. Vertical tail details. The lift curve slope of the airfoil is 5.17 per radian. They've given you span of vertical tail. They've given you area, rudder area, rudder span efficiency factor. The rudder span efficiency factor and for the vertical tail will be the same. Distance from CG to AC of vertical tail, the moment arm of the vertical tail, LVT, is given, and they've given you control surface effectiveness parameter. Now let's look at the first question. What is the aspect ratio of the vertical tail? What is the equation for aspect ratio? B square upon S. Correct? It's the same equation. This is the equation. Let's try doing it. AR is B square upon S. What is B of the vertical tail? 4.23. So this is B. S of the vertical tail, 10.12. Let's try solving this. (4.23) squared divided by 1.768. Just let me know if I'm making any mistakes. Okay, so this is 1.77. All right, aspect ratio. Next question. The lift slope for vertical tail. Lift curve slope of the vertical tail. How do you find this? How do you go about doing this? They've given you the lift curve slope of the airfoil. How do you find it for the tail? Take a moment, try to do this, and then I'll give you the formula and we'll try solving it. Hint is in what I've underlined. Lift curve slope of the airfoil of the vertical tail is given. So how do you find the lift curve slope of the tail? So do you remember that I had told you there's a difference between the 2D airfoil and 3D wing? The difference is that 2D airfoil is considered to be of infinite span. 3D airfoil is finite. And because of the wing tips, because of the uneven flow, that is flow from below the surface of the wing and above the surface of the wing, interact at the wing tip. And there's a reduction in the lift generation, right? So because of that, the CL alpha of 2D airfoil and 3D airfoil is different. How was it different? There was this formula, CL alpha 3D and CL alpha 2D, how they relate, okay? So this is for the airfoil. Let's try doing this. CL alpha 3D. In this case, it's CL beta, just for the airfoil, okay? We're just finding the lift curve slope of the tail. Now, what was for the airfoil? It is 5.17. 1 plus 5.17 by 5 is 1 AR. Aspect ratio of the vertical tail we had found in the previous question, 1.77. Let's try solving this. Can you try solving this? Just substitute the values and let me know. With 2.67, yes, thank you. So it's 2.67. And since everything is in per radians already, since we don't have to change any degree, so it is already in radians. Okay, in per radians. Lift curve slope should be in per radians. This is the mistake. It should be in per radians. Per radians, and it is 2.67. Thank you. Okay. Next question. Find the wingspan of the aircraft. How do we do this? Of the aircraft. So they're giving you wingspan of the vertical tail, not of the aircraft. How do you find it for the aircraft? Wingspan of the aircraft, the span of the wing. How do you do that? Again, take a moment, think about it. We've used this formula before. So just think about it. You can use, so they've given you, look at the first part of the question, look at the details given in the first section above the vertical tail. So in this section, that is the details about the aircraft and the wing, right? So tell me, what parameters can you use from that? What details from there can you use to solve your wingspan? Just read it carefully, take a minute. Exactly, AR1. So you can use your aspect ratio of the wing is B square of the wing, S wing, okay? So aspect ratio of the wing is given as 5.3 and B square wing by S wing, it is 20.4. From here you can find your B wing, which is I'm getting something around 10.4. Let me know if I'm going wrong, but I've got 10.4, okay? Okay, now let's go to the next question. Yeah, so this is the formula that we used. The vertical tail volume ratio, VVT. Now, how do we expand this? What was for the vertical, horizontal tail volume ratio? What was the formula? Do you remember? horizontal tail volume ratio, you had something like, so this was for the horizontal tail, S LT upon C. Yes. So similarly for the vertical tail, what do you have? You have S vertical tail. This is S horizontal tail, area of the horizontal tail, okay? Upon S of the wing. Here LT or the moment arm of the vertical tail, LVT. For this, and here the reference parameter is the span because it's a vertical tail. Okay, so otherwise it was your horizontal tail, you had the chord. Here you have span, you have B. Now you have all of these quantities, I think, right? So SVT you have, yes, S you have, LVT is given to you, and B we just found, B of the wing. So let's just substitute all of these parameters. This is 10.12, S is 20.4, LVT is 4.53, B was 10.4. Let's try solving this. Can you tell me how much is this? Zero 0.216. Yeah, 0.216. I'm getting something like. Okay, so that is close to 0.216. Correct. So this is how you find the vertical tail volume ratio. Okay. Next question. So this was the equation that we used. It's similar to the horizontal tail volume ratio, except the normalizing parameter here is B. There it was mean aerodynamic chord. Okay, just remember that. Rest everything is the same. The rudder control power Cn delta R. In case of longitudinal, it was Cm delta E. Okay, here it directional, you have Cn delta R. The rudder control power Cn delta R is equal to, they're giving you the efficiency factor to be 1. So how do you do this? This formula was directly given to you in the slides. So I'll just put it up here. This is the formula. So let's just substitute. Eta, they've given you as 1. Volume ratio, we just found out to be 0.216, right? 0.216. Cy beta. How do you find Cy beta? What is Cy beta? Tau, you know, only Cy beta is left. How do you find this? How do you find this? What is Cy beta? So you have your vertical tail here. So this is your wing, this is your vertical tail. So Cy beta is something like Cl alpha, right? Cy beta is dFy by d beta, where Fy is the force generated dCy, sorry, Cy, right? So it's like dCl by d alpha. So it's just the lift curve slope. Yes, do you understand that? The only difference here is that for a positive beta, a negative force is generated. So it will be Cy beta is like negative of Cl alpha. Is the negative lift curve slope. Yes? Do you understand that? So the positive beta, here, positive beta will produce Fy, negative Fy. So it is the negative lift curve slope. This is not equal. I'm saying it's something analogous. Okay. Something analogous to the lift curve slope. So it's just the negative of the lift curve slope. Lift curve slope we had found in one of the previous questions. Yes, here. So it was 2.677. So I just substituted. It's negative 2.677 into tau is 0.45. So your final answer, because we know our C and delta R should be negative. So there will be a negative sign and all of your options are negative. That negative sign comes because positive beta produces negative force. Okay. So your Cy beta is negative. Okay. So just find out this. Minus 0.26, correct. Minus 0.26. Perfect. Okay. Next question. The speed of the aircraft during landing is. They've given you CL to be taken, coefficient of lift during landing. They've given you. So how will you find out this? How will we find out this? Coefficient of lift during landing is given to you. They've asked you speed. It's that basic lift equation. Simple lift equation. You know this equation? So they're giving you this and it is during landing. You're assuming trim. So you take V is equal to where lift equal to weight. 2W by S rho CL. Okay, let's do this. How do you do this? 2 into 3225 into 9.81 divided by. So while landing, you're assuming not the cruise altitude velocity density, okay? Sea level density. Oh, S was 20.4. Let me just erase this. .4 density is 1.225. CL they've given you as 2.4. Can you find this? Can you find this value? So I'm getting something around 32.79. Let me know if it's wrong. I've got something around that value. Oh, thank you. Thank you. Sorry. Okay. If the directional stability C and beta for the above aircraft is 0.4146 per radian, C and beta is 0.4146. Notice how it's positive, just like we had seen. C and beta is positive. Why? Positive beta produces negative force, produces positive yawing moment. Okay, positive N. Okay. So if the directional stability for the above aircraft is 0.4146 per radian, maximum allowable rudder deflection is 30 degrees and CL during landing is same as the previous case, 2.4. What is the maximum allowable crosswind speed that can be handled during landing? Read the question carefully. I'm sure you have tried to attempt this during your assignment. And tell me how to proceed with this. Take a moment, tell me how to proceed with this. So just like with the previous two questions that we saw, like moving in the south direction, we will draw the beta triangle. So what do I do? So this is your initial oncoming velocity. This is your crosswind and this is beta. So tan beta is small v, where small v is your crosswind, which is what you're supposed to find out. This question is asking you for what is the maximum allowable crosswind that you can tolerate. Okay, so here they've asked you for this. You know the velocity, correct? You know the velocity, you can find out like this case. And it is in fact the same case, so you can take that. So velocity we know to be 32.79. We need to find out beta. How do we find out beta? This is the question. It's similar to the aircraft moving in the south direction question. How do we find out beta? If we find out beta, substitute here, you can find out the small v, that is the crosswind. How do we find out beta? How do we find out beta? Just like the question that we had seen, aircraft moving in the southern direction. Let me just show you that question. Yeah, so this was the question. This is how it's solved. So can you tell me now, how do we proceed? Let's look at this question. It's a similar question. Right? You use that equation, Cn. So you take the Cn equation, Cn delta R into delta R plus Cn beta into beta should be 0, right? Cn delta R, we had found out, is minus 0.26. Delta R maximum range is 30 degrees. So let's just take 30 plus Cn beta is 0.4146 into beta is 0. So how much is beta? Beta will be let's find out beta and let me know. So it is 0.26 into 30 divided by 0.4146. 30 divided by 18.81. Is that correct? Are you getting? Okay. Thank you. So I substitute this beta here in this equation and find out small v. So small v is nothing but v tan beta. V is 32.79 into tan 18.81 degrees. How do you find this? Tell me the answer. 18.81. 11.17. Yes, I'm getting something like that. 11.169. So it's something around 11. Okay, so that is your final answer. That is the maximum allowable crosswind. Anything beyond your 11.17, your aircraft will not be able to negate. Okay, so the purpose of the rudder is to negate this beta. So anything beyond this crosswind, anything beyond that 18.81 beta, your aircraft will not be able to restore. Okay. Next question. Yeah, so these are the equations that we use. This is equal to Cn. Cn is what is driven to 0 during trim. Okay. Side slip angle for the above case. We just found out. How much was it? They've asked you beta basically. We just found out. 18.82. Correct. That was very simple. Next question. Wing with a sweep has Cn beta. Positive beta gives positive or negative yaw. Cn positive here. So Cn beta is dCn by d beta. Positive beta gives positive yaw. So this should be greater than 0. Greater than 0. Correct. A maneuvering point is defined as the CG location where, this is just the definition. What was the definition of maneuvering point? Which option? 1, 2, 3, or 4? D delta E by Tn equal to 0. What is delta E? I'm just trying to verify that you know these notations, because last class some people had some questions regarding this. So what is delta E? Okay, and what is N? Delta E is deflection of elevator, correct. What is N? Small n? What is small n? During trim, you had lift equal to weight. But during a maneuver, what changes? If I am pulling up, say, will lift be equal to weight? No. How will it change? For a pull-up maneuver, will the lift be equal to weight, will be greater than weight, or less than weight? What will it be? Lift is greater than weight. So for pull-up or any maneuver, lift is greater than weight. So then we define something known as a load factor. Remember, N is load factor. Yes? Yes, so that is what this N is. Okay, so N is the load factor, delta E is the elevator deflection. Okay. Okay, now let's go to the contents of week 6. So this is just a revision of what we discussed in the first 4 weeks. Cm is the pitching moment equation. We have used this equation, we know, Cm naught dCm by d alpha into alpha. The only condition for stability is that Cm alpha should be less than 0. Cm naught should be greater than 0 to trim the aircraft at positive angle of attack. Okay. Neutral point is defined as the CG location where Cm alpha is 0. That is, pitching moment is independent of angle of attack, similar to aerodynamic center. So AC of aircraft. Neutral point is nothing but the AC of the aircraft. Okay. Then we derive the neutral point, the location of neutral point. So this is the equation. Then we studied something known as the static margin. Static margin is the quantity of that tells you how stable your aircraft is, longitudinally stable. It's given by minus dCm by dCl, and the equation is xnp minus xcg, x bar np minus x bar cg. So for a stable aircraft, static margin will be positive or negative. Stable aircrafts, positive or negative, static margin. For a stable aircraft, will neutral point be ahead of CG, behind CG? So your aircraft is something, this is your fuselage reference line, this is your CG. Will neutral point be at this location? This is 1, 2 for a stable aircraft. Will neutral point be at 1 or 2? For stable aircraft. Exactly. So neutral point is behind. For a stable aircraft, this is neutral point. So will your static margin be positive or negative? Look at this equation and tell me. For stable aircraft. Stable aircraft static margin will be negative. So if this is your reference point, this is your X bar CG, and this is your X bar NP, right? So X bar NP minus X bar CG is positive. So static margin will be positive for stable aircraft. Okay. Another way you can find out is that for a stable aircraft, the slope is always negative. Okay. And you have a negative sign here. So static margin is positive. Static margin is the quantity or quantitative way to describe stability. Okay. Then we studied controls. Control surfaces are deflected to trim the aircraft's different CL. It does not change the slope of the graph. It only changes the intercept. So what it does is, this is your graph. It shifts it up and down. So the intercept changes, slope remains same. Okay. Yeah, so more is the stability of the aircraft, more is the static margin, and more is the elevator deflection to change the trim. Okay. So it's more difficult to control a more stable aircraft. Then we studied the equation of the delta E required to trim the aircraft at given CL. This is the delta E required to trim at this any given CL. Okay. Okay. Now we studied, that time we had discussed something known as stick fixed neutral point and stick free neutral point. Just give me a minute. I'll grab some water. Just a minute. All right. Yeah. So now we started looking at the hinge moment. What is the hinge moment? So your aircraft, this is your tail, and your elevator is something like this. So this point along your aircraft is the hinge along which your elevator is deflected. The moment produced at this hinge point is your hinge moment, right? Simple. Now, all of these parameters, S, E, C, E, are all of the elevator, not of the entire horizontal tail, are just area of the elevator, main aerodynamic chord of the elevator. Okay. CH is the hinge moment coefficient. Similar to the previous coefficients, we assume a linear variation with respect to alpha t, delta E, and delta t. Now, CH naught is the intercept as usual. Alpha t is the angle of attack at the tail. Delta E, like you had mentioned, like Suraj had mentioned, it is the elevator deflection. What is delta T? What is delta T? Delta T, what is that? I hope you've gone over week 6 contents. Sir has discussed this extensively. What is delta T? Any guesses? Okay, so there is another structure attached to the end of the elevator. You have another structure here. It's called a trim tab. Now, deflection of the trim tab is given by delta T. Okay. Next, we studied what is the float condition. What is the float condition is when you leave your elevator free, when you're not forcing it to stay at one point, you're letting it to float. So what is the elevator deflection at float, at this float condition? What happens is that there is no hinge moment produced, right? You're allowing it to float freely. So there is no force, there is no hinge moment produced. So your CH is 0. In this equation, when you set CH naught is usually, we can assume it to be 0. And for this case, let's just take the, and you get this delta E float equation. Right? So it's just minus CH. This is 0. Your CH alpha tail has to be 0. Correct? For your CH alpha tail to be 0, what are the two methods that sir discussed? Now, if this is your horizontal tail, and if this is your hinge point, this is your CP, and this is your hinge. All forces are presumed to act at the CP. They do act at the CP, center of pressure. Okay. So now there is a hinge moment because there are forces produced here, lift and drag, which act at the hinge. Okay. Now, if you want your hinge moment to be 0, if your CP and hinge point are the same, then there is no moment. Right? There are forces, but they're acting at the hinge. So there is no moment at the hinge. That is one method. Another method is something that sir told. It was referred to as horn balance. So this is your entire vertical horizontal tail. Okay. And this is the deflectable portion. This is your elevator. So usually it's only towards the end. Now you keep some area here which can be deflected too. So if this is your hinge point, all the forces acting in this area, in this and this, will produce a restoring moment. This area will produce, okay, so the crossed out, the slanting lines that I've drawn on the surfaces, that area will produce a hinge moment in this direction. And the ones that are colored out, ones that are shaded out, will produce a restoring hinge moment. So they will cancel out each other and your effective hinge moment will be 0. So these are the two methods to ensure that your delta E float is 0. So your elevator floats at 0 degrees, no deflection. Okay. Okay. Another point to note here is that CH alpha tail, CH delta E, CH and CH delta T, they are all less than 0. Why? So now you have, this is your horizontal tail. This is your elevator. That's your hinge point. Right? Hinge. Now, if you have angle of attack, change in angle of attack, alpha tail, it increases the forces here. There's a delta L, right? Which produces a nose down, anti-clockwise movement at the hinge. So, positive alpha tail gives you negative hinge moment. Your CH alpha tail is negative. Next, if I deflect my elevator down, so if I deflected elevator down, it is positive. Deflection of elevator down is considered positive. So if I deflect my elevator down, camber is increased, lift is increased, delta L. Again, you produce negative moment at the hinge. So your CH delta E is also less than 0. Now similarly, delta tail, delta trim tab. Again, you deflect it down, positive deflection produces negative hinge moment. Okay. So all these three parameters are less than 0, all these three derivatives. Okay. Then you have some conventions regarding the sticks. Okay. So if you push your stick forward, pushing the stick forward increases the velocity. Now, if you need to maintain the same trim, same properties, when you increase your velocity, what should you do? You need to reduce your CL, right? You need less CL. How do you get less CL? You need to have less alpha tail. And how do you get alpha tail less? By deflecting your elevator down. If you deflect your elevator down, let me draw this. If I deflect my elevator down, you increase your delta L, produces pitch down moment, and which reduces the angle of attack seen at the tail. Okay, the angle of attack seen at the tail will be reduced if you deflect your elevator down. Okay, so when stick pushing forward is delta E down. All right. Okay. Then another point to be noted here is that delta E required, the equation that we saw here, this equation will always be governed by stick fixed neutral point. Let me emphasize that. Will always be governed by stick fixed neutral point. It will never be stick free. Okay, it will always be governed by the stick fixed neutral point. Okay, stick fixed static margin, stick fixed neutral point. Okay. Now, there are three conditions that are discussed. If your freely floating elevator is already at the delta E required condition, then the pilot need not apply any force, stick force is 0, so the aircraft is neutrally stable. Now, if your freely floating elevator is less than the required elevator angle, so it's not at the same condition, the pilot needs to apply some force. What force is required? You need to pull the elevator, you need to push the elevator up. So what do? Depending on your sign convention, you need to pull your stick. Pull your stick, elevator is deflected upwards, and the delta E float matches up to the delta E required. Reverse is the condition for when the delta E float is greater than the required angle. All right. So these are the three conditions that Sarah discussed in the class. Then stick force Fs is governed by this equation Hm delta E Ls delta S. What is Ls and delta S? Delta E is elevator deflection. Hm is hinge moment. What is Ls and delta S? I hope you've gone through the lectures. So you should know what Ls and delta S are. What are they? What is Ls delta S? So sir had mentioned something like the stick force, right? So this was so pulling and pushing the stick about a point. If you pull it, it goes something like this. Now this length is known as Ls, and this deflection is delta S. Right? CL alpha tail into alpha tail, CL delta E into delta E. Now, if it is hands-off condition, that it is freely floating, your CLT, excuse me, yeah, your delta E will be delta E float. I just replace that equation. When you solve this, you get that the CL tail, the CL alpha tail is changed. That is the only difference between stick fixed and stick free. For your stick fixed case, it will be CL alpha tail. For stick free case, you will have the CL alpha T prime. Okay. Similarly, for the neutral point and your static margin, they will change. All right. Now your DCM upon DCL fixed, is it positive or negative? DCM upon DCL is something related to static margin. Is it positive or negative for a stable aircraft? Yes, it's negative. So more the negative it is, more stable your aircraft is. All right. Okay. Now let's look at this term. Let's see if it's positive. VH is positive, efficiency factor is positive, CL alpha tail is positive, CL alpha wing is positive. This entire term is positive. Tau is positive. CH alpha tail, positive or negative? CH alpha tail, positive or negative? We just saw that CH alpha tail, CH delta E, CH delta T, they are all negative. Okay, so this is negative. CH delta E again is negative. So this entire term is positive, right? So we saw that the CM, DCM upon DCL, more negative it is more stable. Now your negative value is being reduced. It's becoming less negative. So what it means is that stick free case is less stable than stick fixed case, right? The negative value is reducing. It's becoming less negative. So your stick free is less negative than the stick fixed, which is why your stick free case is less stable than your stick fixed case. Okay. Okay. Now this is just a comparison between the stick fixed and stick free case where it's shown that the only difference is in that CL alpha. Okay. So now let's look at CMCG, the moment at the CG. For stick fixed case, we know this term, right? For a stick free case, only this CMCL changes, DCM upon DCL. DCM upon DCL, the new one is here. That changes. Okay. Next, CM naught. Everything is same. All that changes is that CL alpha tail becomes CL alpha tail prime. CL alpha tail prime is given by, so this quantity is CL alpha tail prime. Okay. That is the only difference. Then DCM upon DCL. This is the equation. The only difference again here is CL alpha tail prime. Okay. Next, X bar NP. So there is a bar above all of this. All right. The only difference in this case again is that CL alpha tail becomes CL alpha tail prime. That is the only difference. So DCM upon DCL changes, CL alpha tail changes. That is the only difference between stick fixed and stick free case. Okay. Okay. Now let's look at a few questions. In the figure below, which aircraft will have higher stability margin? Stability margin, static margin? Just look at the aircraft, look at the graphs and tell me which one will be more stable. Which one will be more stable? How do you define stability? For a longitudinal case, how do you define stability? DCM by DCL, yes. So your graph is CM versus CL. So now you can tell me which aircraft is more stable, whichever has more DCM, that minus DCM upon DCL. So your stability margin or static margin is minus DCM by DCL. So whichever has more static margin is more stable. So which aircraft has more static margin here? B, exactly. The slope of the B graph is higher. The magnitude of slope is higher. So the B aircraft is more stable. Correct. Okay. Which airplane has more control power? Control power is CM delta E. Okay, so which aircraft has more control power? The graph is between CM and CL, but they've given it to you for two elevator deflections. So which graph has more CM delta E? A. Can you tell me how? Let's find out CM delta E for both of them. For A, okay. CM delta E is DCM by D delta E. Now, what is the change in CM? 0.2 minus 0.1. Correct? What is the change in elevator? Take it at any point, okay? Just take it at any point along this. Okay, I'm taking it at the first point because it's convenient. Okay, so it's 0.2 minus 0.1. And what is the change in the elevator? It is 10 minus 0. So this comes to 0.01. Now let's do it for the B aircraft. Again, you can take it at any point. I will be taking it at the first. So Cm delta E is dCm by d delta E is 0.4 minus 0.2 by 10 minus 0. Okay, how much will this come to? 0.02. So which aircraft has more control power? B, exactly. Okay, so this is how you answer such graph questions. Try to find out the term that is given to you exactly. It's more often than not the slope. Okay, let's go to the next question. When aircraft trim speed is changed from 60 to 100, maintaining the same altitude, the elevator will float more or less. Read the question carefully. When the aircraft trim speed is changed from 60 to 100, the elevator will float more or less. So what happens here is that your speed is increasing, right? So velocity is increasing. When you have to maintain the same altitude, what do? If the velocity increases, we need to reduce your CL. Correct? Is that clear? Yes. How do you reduce your CL? You have to reduce your angle of attack. So alpha tail has to reduce. Correct? Yes. How do you reduce your angle of attack? How do you reduce alpha tail? You deflect your elevator, right? How do you deflect it up or down to reduce angle of attack? You have to do delta E. Should it be up or down? To reduce angle of attack at the tail, do I deflect my elevator up or down? That is the convention. Yes, Sandra, you're right. Deflecting it up is for negative. But if I have to reduce my angle of attack, do I deflect my elevator up or down? To reduce alpha tail, delta, exactly. Delta E should be deflected down, right? So that is positive. Positive delta E. Okay. So keeping that in mind, we go to this equation. Okay, elevator float. Elevator float is this. Okay. Now we know. So let's take it at the first condition. So alpha tail 1. So for the first condition, your alpha tail 1. Let's just take CH delta, this to be 1 and this to be 1. Okay. So at the first condition, if your alpha tail is say 1, and the second condition, your alpha tail is increased, right? So it becomes, sorry, I'll start again. For your first condition, when it's flying at 60, let's take it to be 2 degrees. For your second condition, let's take it to be 1 degree, correct? When you increase your velocity, you need to reduce your angle of attack, right? So how much will be delta E float here if both these derivatives are 1? Here it will be minus 2 degrees. Here it will be minus 1 degrees, correct? Which is more? Magnitude wise, how much do you have to deflect your elevator? Here you have to deflect less, right? Here you have to deflect it more. I'm not saying the degrees. You have to deflect your elevator by 2 degrees in the first case. That is when it is flying at 60 meters per second. When it's flying at 100, you need to deflect your elevator less. Right? Is this clear? Yes. Okay. Let's go to the next question. To reduce the floating tendency of an elevator, hinge line has to be moved aft or forward. So this is your vertical tail. And this is your elevator. This is your hinge point. And this is your CP. To reduce the floating tendency, should your hinge line be moved aft or forward? To reduce floating tendency, we discussed 2 methods. One is horizontal hinge line and CP should be at the same point. Another one is horn balance. Horn balance is not being looked at here. Now you're looking at hinge point and CP. So to reduce your floating tendency, should I move the hinge point towards CP or away from CP? If I move it towards CP, the momentum becomes less and less and less until it becomes 0, right? So then the floating tendency is reduced. Yes? Yes? Okay. So this is say case 1 and this is say case 2, where your hinge point is here and CP is also here. In which condition there will be float? Here there will be more float, right? More float. Here there will be no float, 0 float in fact. Correct? So we had discussed this. Let me discuss this. Yeah. So if your CP and hinge point are at the same, then you will have no moment. So no floating tendency. Correct? Your delta E float will become 0. So if I move in this case, if I move my hinge point towards CP and it becomes at the CP, I'm reducing the floating tendency. The delta E float becomes closer and closer to 0. Correct? Because there will be no moment produced. Yes. So it has to be moved aft. Okay. So I think we'll end the class here. So does anybody have any questions? Okay. If not, all the very best for your assignment 6, and we'll meet again next week, Tuesday, and we'll discuss the assignment 6 questions. Okay. Thank you. Thank you. Thank you. Thank you very much. Okay, so we'll end the session here.